Hello. Our objective today is that we're going to estimate the area under of a function using rectangles. The reason we need to use rectangles, of course, is that this shape is not something that we have a formula for the area for. So if we can break it into something that is close to a shape that we have an area for, like rectangles, then we can use the formula for that area, base times height, to estimate the area of this shape. So we're definitely estimating, we're approximating, we're not going to find it exactly. And we'll talk at the end about how to know how good your estimation was. So in our first example, they're asking us to estimate this area using 5 right endpoint rectangles. We'll get to right endpoint in a moment, but 5 rectangles from t equals 0 to t equals 10. So you notice that the distance or the amount of t traveled from 0 to 10 is 10 units. And they're asking us for 5 rectangles. So if we're going 10 units and 5 rectangles, then if you divide this, that means that each rectangle is going to be 2 units wide. The analysis that I did here is not something you would need to write every time, but this idea is important here. So our first rectangle is going to go from 0 to 2, and our next one is going to go from 2 to 4, and then from 4 to 6, you notice they're all distances of 2, from 6 to 8, and then finally from 8 till 10. So you see, this is going to end up with 5 rectangles, and also we go the entire distance from 0 to 10. Unless it tells you otherwise, it's implied all the rectangles are going to have an equal sized base. Now the right endpoint is tells you the height. So the fact that it's on the right means, I'm going to switch colors here. It means that in this first rectangle, I could either use the height on the left side or the height on the right side or the height in the middle. And we use the height on the right side because it told us to. So in this first rectangle that goes from 0 to 2, the height on the right side of it, sorry for my writing, seems to be about here. So again, I'm sorry for the bad drawing, but I went on the right side, I went up to the function, and I went across, and maybe this would be a little bit better. This appears to be a height of about 8.5. So I'm going to jot that down right here. The next one, if I go from 4, so from 2 to 4, the right side of that is 4. If I go up from 4 to the function and I create a rectangle there, that height seems to be about 10. So first rectangle, the right side had a height of 8.5. Second one on the right side had a height of 10. I'm going to keep changing colors and keep doing this. This next one, maybe just a little taller, let's say like 10.2. Just estimating here, of course. Next one from 8 up. Maybe that's 10 again. And then the last one from 10 on the right side of that last 5th rectangle. Let's say that that's, I don't know, 9.2. I'm just estimating here. I'm clearly not doing a great job. But these 5 rectangles together create an approximation to the area that they asked for. So what we can now do is add up that area using just a bunch of base times heights. So that first rectangle has a base of 2 and a height of 8.5. I like to put these in parentheses, totally optional, but 2 times 8.5, that represents the first rectangle. And then we're going to add the area of the second rectangle that also has a base of 2, and this one has a height of 10. So I'm going to say 2 times 10. The third one has a base of 2 and a height of 10.2. The fourth one has a base of 2 and a height of 10. And then the fifth one has a base of 2 and a height of 9.2. So I've got 5 rectangles, 1, 2, 3, 4, 5. They each have a base of 2 and they each have a different height. You notice you could have, if you had been thinking ahead, you could have factored the 2 out first, and you can always do that if they're all the same, and that's fine. What I'm doing now is typing this into the calculator. And when I do that, it comes out to 95.8. So our estimated area here is about 95.8. I just realized I should have said estimating, because this is definitely not the area of that curved shape. It's just an estimation of it. Our next example. you notice this is a little bit nicer because they gave us the y value. So maybe you don't see the picture, but now I know that it has an exact y value of 12 and 5 and 3 and 6 and 0 at each of these x values. So using the table to the right, estimate the integral using left endpoint rectangles. So in a case like this, we're just going to use the table as given. This is actually going to be, as I said, a little bit easier. So in the previous case, the bases were what I call the change in x. So delta x or dx is the change in the x value. And for each one of those, it was 2. If you look here in this next example, the change in x's are different, and you can see them in that top row. So from 5 to 8 has a change of 3, 8 to 11 has a change of 3, 11 to 14 has a change of 3, and then 14 to 17 has a change of 3. So in this case, all of our bases of our base times height are going to be 3. Then they said we're using left endpoint rectangles. So this first rectangle goes from 5 to 8, and on the left side, it has a y value of 12, and on the right side, it has a y value of 5. Since they said we're using the left endpoint rectangles, this rectangle we're using with its height on the left side. So our first base times height is base is 3 times the height is 12. Our next one goes from 8 to 11. The height on the left is 5 and the height on the right is 3. And so since we're using left endpoint rectangles, our base is 3 and our height is 5. So I'm going to add 3 times 5. Our next one goes from 11 to 14. The base is 3, change from 11 to 14, and our height on the left is 3, our height on the right is 6. Since we're using left endpoint rectangles, we're using that height of 3, so this will be 3 times 3. And then finally, our last one, our base is 3, and our height on the left side is 6. You notice that 0 is not going to be used in this case. So we're going to add 3 times 6. Again, all these have the same bases, so if you wanted to go a little bit faster, you probably could have factored that out. But I'm just going to type all these into the calculator right now. And this comes out to an area of 78. This is still an estimation, but I'm putting an equal sign here because all this that I wrote down does actually equal 78. But it is an approximation of whatever this function was. Notice that 0 we did not use. You never use the rightmost y value in left endpoint rectangles, and then it would have been the opposite if they had asked for right endpoint rectangles. The 12 we never would have used. Last example here is honestly just kind of annoying, not harder. Notice that they gave us a function here, and they asked us to estimate the area from 1 to 2, which is a distance of 1, from 1 to 2. Using 4 rectangles with right endpoints. So if we go from 1 to 2 with a distance of 1 using 4 rectangles, that means each one rectangle is going to be 0.25. So obviously we don't have a table here, but we can make one. It's not the hardest thing in the world. We need to go from 1, sorry, I probably should have put an x in front, from 1 to 2, counting by 0.25. So 1, 1.25, 1.5, 1.75, and then if you do this right, excuse me, if you do this right, you should end where it said to end. So it's going to end at 2. And then to find our y's here, this is what makes this a little bit more work, is we just need to find the y value for this function at each of these x values. So I'm going to do this in a thought bubble off to the bottom. You probably don't need to write this. I'm going to find f of 1 and f of 1.25 and so on, and just type them into the calculator. So I'm typing 2 times 1 minus 1 squared, which comes out to 1. So the y value at x equals 1 is also 1. And then I'm just going to do this again for each of the x values that I laid out in the table. So the next one, I'm going to round each of these to 3 decimal places, is 0.938. 1.5 is going to be 0.75. 1.75 comes out to 0.438. And then finally, when I plug in 2, comes out to 0. Once you've got this done, it's basically the exact same as the previous problem. So we've got, let's see, it said right endpoints. So each of our dx's, our change in x, looks like it's about 0.25, which we had calculated earlier. I'm not going to keep writing it, but that's the 4 changes. And then if we're using the right endpoint rectangles, then in this first rectangle from 1 to 1.25, the y value on the left is 1, and on the right is this 0.938, so we're going to use that one. And then in the next rectangle from 1.25 to 1.5, the y value on the right is that 0.75, so we'll use that one. The next rectangle, the y value on the right is the 0.438, and then the last one, the y value on the right is 0. So that 1 initially will never be used. So our approximation here is going to be all of our base times height. I'm going to think ahead a little bit. Since all the bases are 0.25, I'm going to factor that out to save myself some time. And then just add up the height. So 0.938 plus 0.75 plus 0.438 plus 0. I'm going to type this on in the calculator, and this will give us the answer. When I type all this in, I get 0.532. So that's the approximate area under this curve from 1 to 2. All right, finally, we are going to determine if a Riemann sum estimation is too high or too low. And here's what I want you to do. First, can you draw a function that is increasing and draw it 2 times? Then underneath it, we're going to draw just in each one, just draw a single rectangle with a height on the left and a height on the right. And we're going to see what is too high and too low. So in this first one, we're going to draw the height on the left. So we've got a left height and a right height. If we use the height on the left, you'll notice that this is too small. It's missing that shaded area. And if we use the height on the right, then this is too large. We've got that extra shaded area. And that's going to be true for any increasing function. So this fact you can always analyze yourself, but it'll always hold up. So what we're going to write is, if a function is increasing, then left rectangles will be too low, and right rectangles will be too high. That will always be the case. That's the only thing you need to consider. The last thing we're going to do is analyze this again with decreasing, and you can probably already guess, but this is just going to have the exact opposite conclusion. So I drew 2 graphs that were decreasing, same graph, and when you draw in a rectangle using the left height, the height on the left, it's a little bit too big. So left rectangle, if the graph is decreasing, is a little bit over. And then drawing in that same rectangle on the right, it's missing this little area. So the right is a little too short. So last thing we're going to write, if a function is decreasing, then this is reversed. You can write it all if you want. So that's the only thing you need to look at to answer a question like this is the function increasing or decreasing? And then you can answer if the estimation is too high or too low.